Alright, this is going to be the first video of a series, and today in this video we're going to cover organomagnesium and organolithium compounds. We're going to cover lithium diorganocopper, Gilman reagents, and carbenes or carbenoids. So, these compounds fall into a class called organometallic compounds, and these compounds usually are shown as having a carbon to metal bond. So therefore a organometallic compound. And we're going to focus on lithium, magnesium, and copper in this video. But other reagents are available, such as zinc, boron, and aluminum. But we're going to focus on these three because they are the most significant historically in organic chemistry. These reagents are very important in the reaction of carbonyl compounds and cross-coupling reactions, but we're not going to get into that today. That might be a later video. So, let's start with organomagnesium compounds. You might see these more commonly referred to as Grignard reagents. So the RMGX will be the most common kind of formula you would see for this, where X is going to be bromine, iodine, or chlorine. And the oxidation state of this magnesium is going to be 2+. R is just whatever compound this is attached to. So this compound is generally prepared via a slow addition of an alkyo or alkynyl halide to a suspension of a slight excess of magnesium metal in diethyl ether or THF, tetrahydrofuran. Something that you might see to synthesize a organolithium magnesium compound is going to be something like this. So this is 1-bromobutane, and we're just going to add magnesium to this in ether, and this is going to form a compound that looks like this. And this will be butyl magnesium bromide, and this will be our Grignard reagent. So some common starting materials are bromides with oxidative addition of magnesium. And something to note for Grignard reagents is that there is usually an equilibrium between the monoalkyl and dialkyl magnesium. So they would be, these two would have equilibrium usually. RMGX will be in equilibrium with R2Mg plus MgX2. That will be in equilibrium. This usually forms on the surface of metals, and it is usually dissolved as a coordination complex solvated by ether. The magnesium would act as a Lewis acid, and the ether acts as a Lewis base in this case. All right, let's move on to organolithium reagents. You're usually going to see them with the formula something like that, and this would usually be, prepared by treating an alkyl arrow or alkynyl halide with a 2 equivalent of lithium metal. And the oxidation state of this lithium is going to be +1. So the example that I can give for this is, this is 1-chlorobutane. We're going to add a 2 equivalent of lithium in pentane. And this is going to form butylithium. And this butylithium is a very reactive compound as a very strong nucleophile. It's a nucleophile in carbonyl addition reactions, and it will act as a nucleophile even at very low temperatures. Another thing to note that this compound would be usually used under an inert atmosphere of nitrogen or argon, since they will very rapidly react with atmospheric oxygen and water. So, let's talk about both of these, organomagnesiums and organolithium compounds. So these usually would behave as carbenions in their reactions, in which their carbons have an unshared pair of electrons, and they will usually bear a negative charge. And these carbon metal bonds are polar covalent bonds. During the preparation of Grignard and organolithium reagents, the carbon atom bearing the halogen is transformed from an electrophilic center to a nucleophilic center. So, let's say something like this. There will be two hydrogens. I'm just not gonna go with the stereochemistry, but these two hydrogens would be on opposite sides. It's carbon attached to a bromine. This is going to be a electrophilic center. This, excuse my handwriting, electrophilic center. But if we add Mg to this, it's going to become something that looks like this. This carbon is going to get turned into a nucleophilic center. Just wanted to make sure that I got everything correct. So the consequence of this is that this is going to behave as a carbon center nucleophile, so it will react with the electrophilic carbons of the carbonyl groups of aldehydes, ketones, carboxylic esters, and acid chlorides. And this mainly would enable the formation of new carbon-carbon bonds. Go over to reactions of these RMGX, organomagnesium compounds, and organolithium compounds with protic acids. So both of these compounds are going to readily react with any sort of proton donor stronger than the alkene from which they came from, and because both of these compounds are very strong bases. So something like this would be a stronger base than if we have, say, water. This is going to react with it to form a weaker acid and a weaker base. So, but both of these will not be able to be prepared from any organohalogens that contain one of these functional groups or a nitrocarbonyl group. So this, if any organic halogens contains a functional group with a stronger acid that is going to form a weaker acid, this will react with itself and it will destroy itself. All right. Now we're going to talk about the Grignards in a acid-base reaction as a strong base. So let's try something like this. If we have a Grignard reagent, something like this, MgI, with a alcohol, it's going to, it's pKa, let's say it's 16 to 18. This is going to form a alkene, and a magnesium alkaloxide, alkoxide. Excuse me. So that's another example of a strong base. The RMGX acting as a strong base. But this can also, these Grignard reagents and lithium compounds can also react with oxiranes. So this is going to say we have butyl-magnesium bromide, and if we react this with ethylene oxide, it's going to form magnesium alkoxide, and if we quench it with an acid, any proton source, it's going to form an alcohol. It's going to form 1-hexyl. So notice how we actually added these two carbons to this compound and formed an alcohol. So this is a way of extending our carbon chain. If we react such a compound with a substituted oxygen, so let's do something else. Let's say we have phenylmagnesium bromide. If we have phenylmagnesium bromide, these should be swapped over. I keep writing the bromine first, but it should ideally be, let's actually change that. All right, if we react this with a substituted oxygen, something like methyl oxygen, it's going to form a magnesium alkoxide again. Excuse my drawings, I'm still not very good at these. These are not, just another thing I want to know, that there is no bond between these. these just stay near each other due to their attraction of charges. And if we were to crunch this compound with acid, proton source, it's going to form 1-phenyl 2-propanol. It's going to form another alcohol. Also, I should mention that the major product would correspond to the attack on the less substituted carbon. So this carbon right there. It's kind of like an SN2 reaction. So, let's do some examples of how to prepare an alcohol from a organic halogen compound from an oxygen. So, if we had something like this, how would you prepare this? And something like this, how would you prepare that? Let's call this A, and let's call this B. How would you prepare these two compounds from a organohalogen compound and an oxygen? All right, so compound A is going to be produced from, relatively simply, from something like this, bromine with an oxygen. Sorry, the name escaped me for a moment. And this, the reaction is going to undergo something like, look something like this. Br going to react with Mg in ether, and it's going to form our Grignard reagent. And we're going to react this with the oxygen. I'm probably saying that wrong, but I'm not great with names. And this is going to form our desired compound as a major product. This second compound, compound B, is going to be formed from something like this. And the reaction is going to look like this. So let's go back to another question. If we treat a compound, say 4-bromo, 1-pentanol, if we were to treat this compound with magnesium and ether, what would happen? So this compound will actually not form a desired organolithium, well, organomagnesium. Let's just switch this over to lithium and pentane. But it wouldn't work with magnesium either. If we treat this compound with lithium, it would not generate the desired organolithium reagent, because this OH group is going to react with, if we were to form this compound, lithium bromine group, and it's going to do the dissociation up here. That looks like this, and it's going to destroy itself. So a compound with a functional group that like this with a pKa is going to not be able to react and form a organolithium reagent. All right. Let's talk about lithium diorganocoppers. Otherwise known as Gilman reagents. So this reagent is usually prepared by using organolithium reagents. So it's prepared by treatment of alkyl-arrow or alkylolithium compound with copper iodine. So copper 1 iodine. So something is going to look a little something like this. If we have, say, butyllithium, a 2 equivalent of butyllithium, no. Lithium, and if we were to add that to our copper iodide under ether or THF, it's going to form our lithium diorganocopper. This part is going to be the same as this part right here. So the two organic groups of this compound associated with a copper, the oxidation state of this copper is 1. It's going to be a 1+. And this is going to give a negatively charged species. The reason why this lithium ion is associated with this negatively charged species is to act as the counter ion. All right, let's go over the coupling of Gilman reagents with organohalogens. So, Gilman reagents, like the other reagents, also form new carbon-carbon bonds, but this is formed by coupling with alkyl chloride, bromine, or iodine. So only one of the Gilman reagents, alkyl groups, is transferred in the reaction. The stoichiometric in copper, equivalent copper, is 1 equivalent. Because Gilman reagents are prepared from halides, this leads to a pretty effective coupling of 2 halides. So if we were to have, let's go crazy, 2 of this, 2 equivalent of 1 idodecane and we form a Gilman reagent off of that. Pentane and copper iodine. We're going to form a Gilman reagent. And if we were to add this to, say, 2-bromopropane, it's going to add that onto the end there. I just realized I was thinking so hard, but yeah. Maybe I shouldn't have done such a long chain. I feel like I'm missing carbons, but you get the gist of how this works. So, Gilman reagents are prepared from methyl alkyl vinylic and aryl halides via the corresponding organolithium compounds, given the best yield of coupling products. So yields are lower than secondary. Yields are lower with secondary and tertiary haloalkanes. Coupling with vinylic halide is stereospecific, so configuration of these carbon-carbon double bond is preserved. If we have that with a lithium dibutyl copper, either THF is going to form something like that. So let's go with an example. I'm not gonna draw, I'll draw them out actually. So let's go with example. How would we convert 1-bromo cyclohexene to 1-methyl cyclohexene using lithium thiogranate copper reagent? How would we do this? So 1-bromocyclohexene is going to look like this. And in order to convert it to 1-methyl cyclohexene, we're trying to have to replace this bromine with a methyl group. So in order to do that with the lithium thiogranate copper, we're going to need a methyl on this lithium thiogranate copper, and it's going to convert that into a methyl group. Alright, let's go over the reaction of a Gilman reagent with oxygenes. So this will also produce new carbon-carbon bonds, but this results in a reduced selective ring opening of substituted epoxides at the less substituted carbon. As before, it also goes to the less substituted carbon, and it gives alcohols. So let's do an example. Let's give an example. So if we were to treat it's really ugly, let me redraw that. This is styrene oxide with a organolithium compound, diorganolithium, a Gilman reagent, with a double bond, something like this. As before, in order to quench the solution, you would have to use the proton source. It's going to form something like this. Where this is going to be added onto the end there. Let me see if I can make this clear. Like that. This ring is going to open, and we're going to end up with something like that. Let's do another example for. So what are the two combinations of epoxides and the Gilman reagents that can be used to synthesize 1-phenol-3-hexanol, which is going to look like this. What are the two combinations of epoxides that can use to be synthesized this? So we can either use we can either attach the phenol group like so in a Gilman reagent with a Gilman reagent, and something like this, and our epoxide, or we can attach the extra carbon chain with the Gilman reagent. Both of these reactions will result in that compound. All right, let's do another example. What is the product of if we were to treat this compound with 2 lithium pentane and copper iodide in ether and this compound here. So this is going to result in a compound that looks like this, where this is what your originally is, and this is where you're attaching. You're forming a lithium diorganocopper compound, and with that, you're going to add this compound onto here. All right. I might do some more examples in a separate video, but in this video we're just going to do just a few. So let's go over carbenes now. So carbenes are neutral molecules containing a carbon atom surrounded by only 6 valence electrons. So the formula is going to look like that. This will be a carbene. This compound is highly reactive and it acts as an electrophile. And because they are electrodeficient. The simplest carbene is methylene. And this is prepared by photolysis or thermolysis of diazomethane, which is diazomethane is going to look like this: C2H2N2. So the formula is going to be that. Let's actually go over the reaction mechanism of this. So this double bond is going to go over there, and those 2 electrons are going to go into the double bond, and this is going to form intermediate that looks like this. And if we were to treat this, it's going to form methylene. The carbon back group is going to break off, and it's going to form this nitrogen. So this being a carbene, this carbon is going to be sp2 hybridized, and this pair of electrons is going to occupy the 3rd sp2 orbital in the lowest electron state of most carbenes. But usually carbon is sp2 hybridized with a vacant 2p orbital. Methylene in this electronic state combines features of carbocations and carboanions, in that it has both a vacant p orbital and a lone pair. Let's go over and let's go through dichlorocarbenes. So, dichlorocarbene is going to be more selective and more stable and chemoselective than free methylene, because resonance stabilization with the lone pairs on the chlorine satisfy the electron deficiencies on the carbon. So these chlorines, that's a carbon, that's a chlorine, and chlorine is going to do resonance stabilization with that carbon in the center. These dichlorocarbenes are usually prepared by treating chloroform with potassium terbutoxide and removing HCl. So it's going to be chloroform. It's chloroform and potassium terbutoxide. And that is going to remove the HCl and form a terbutyl alcohol. So dichlorocarbenes will react with alkenes to give dichlorocyclopropanes. So if we have a dichlorocarbene here, and if we were to add it to that, it's going to form a dichlorocyclopropane. If we add it to the alkene, it's going to form this cyclopropane. It's going to look like that. The addition of a dihalocarbene to an alkene, dihalocarbene, so dichlorocarbene in this case, to an alkene, will always show syn stereoselectivity, so it will always be like that. The reaction of a cis or trans alkene with a dihalocarbene gives you only a cis or trans dihallocyclopropane respectively. So this is syn selective. Let's go through the formation of a dichlorocarbene and its reaction with a cyclohexane. The carbon is terbutoxide. This terbutoxide is going to take away this hydrogen from this chloroform. So this is going to attack the hydrogen of this chloroform, and it's going to form this alcohol, this terbutyl alcohol. And this trichloromethylide ion. So this is actually two steps. This anion, sorry. And this bond is going to actually break. And it's going to give a more stable molecule or ions. It's going to turn into this. That's the mechanism for the formation of a dichlorocarbene. And if you were to take this dichlorocarbene that we just formed, and we were to react it with cyclohexane, the same one that we had before, this is going to attack that, like that, and it's going to form a dichlorocyclopropane, the same thing we had before. This will be pointing the same way. I'm not going to go over the examples for this one, but I'm just going to skip over to the Simon-Smith reactions. We're going to go over Simon-Smith reactions now. So, the addition of a methylene to an alkene is the Simon-Smith reaction. Recall that methylene prepared from diazomethane is not synthetically useful. This uses diazomethane and zinc dust, activated by a small amount of copper, to zinc and copper coupling to produce methyl zinc iodine. Methyl zinc iodide in reaction similar to a Grignard reaction. So we're going to have diadomethane, CH2, I2. This is our diadomethane, and it's going to be reacted with a zinc and copper couple in ether, usually, to form our isomethyl zinc iodide, which is going to, the formula is going to look like that. This is a Simon-Smith reagent. A Simon-Smith reagent will react with a very wide variety of alkenes and is going to form cyclopropanes. So this is a Simon-Smith reagent. So if we had, say, methylene cyclopentane with our Simon-Smith reaction, diadomethane, and we're gonna react it with our zinc and copper couple in ether, it's going to form a spiral, a compound that looks like this, plus the zinc and iodine. This is actually spiral 4,2 heptane, but it's going to form this cyclopropane there. If we have a compound that looks like this, for example, instead with this Simon-Smith reagent, and it's going to form a compound that looks like this. This is going to actually form a racemic mixture of both of these, of this and this. So Simon-Smith reagents react directly with an alkene by a concerted mechanism to give the cyclopropane containing product. That's because it is more selective than free methylene, which is it's stereospecific. This is an example of a carbenoid, and carbenoids are compounds that deliver the elements of a carbene without actually producing a free carbene. So the mechanism of action is going to look something like this for the Simon-Smith reagent is going to look like this if we were to have, say, that there. It's going to go for the carbon. This bond is going to go to the bond, and this bond is going to go to the zinc. And this is going to form our zincine and this cyclopropane. So let's go over a problem for the Simon-Smith reaction. How would you convert 1-bromo, 3-methyl, butane into 2,7-dimethyl octane? And you must use 1-bromo 3-methyl butane as the source of all carbon atoms in the target molecule. And this is our 1-bromo 3-methyl butane into 2,7 dimethyl. Sorry, I was just counting the carbons there. octane. How would you convert this into that? So the solution to this is the coupling of a Gilman reagent with the starting bromoalkene. So this is going to actually have 2 intermediates and 3 reagents. This 1-bromo, 3-methylbutane is going to be reacted with 2 equivalent of lithium, and it's going to form this compound there. And if we react this with 0.5 equivalent of copper iodide, it's going to form this diorganocopper lithium compound. And this can be added to our starting product, starting compound, the 1-bromo-3-methylbutane, and let's move this actually. It's going to be added to that, and this will actually form our desired product, which is our 2,7-dimethyl octane. Alright, that's it for everything that I'm going to go over today. This is my first video, so this video is mainly used for myself to study, but if you like anything, just let me know, and I'll probably go over it.